Right, I'm going to try to make a connection between our specific expression for gravitational potential energy near the surface of the Earth, mgh, and gravitational potential energy from the general expression, the one that's always true. So minus g, product of the masses, divided by the distance separating their centers. So let's have part of the surface of the Earth and Earth's radius r sub e. Let that give us our initial point around the surface of the Earth, and then also some delta y up for our final point. So the change in gravitational potential energy between the final and the initial is delta U sub G is UG final minus UG initial. Putting in our general expression for gravitational potential energy minus G mass of the Earth, my mass, over raised to the Earth plus delta y. So when I'm up here at my final point, and then I'll have a minus minus, which is a plus, G mass of the Earth times my mass, interacting over a distance of the rays of the Earth from when I was at my initial point. I'm just going to factor that a little bit, pull out common constant of gravitation, mass of the Earth, and my mass. And then we'll start trying to get some insight. One over raised to the Earth from this term, and then minus 1 over raised to the Earth plus delta y from that term. Okay. I'm going to give everything a common denominator for the two terms in the parentheses, so I'm just going to cross multiply. I'm going to have the radius of the Earth plus delta y, and cross multiplying this way is going to give me a minus radius of the Earth, and then the common denominator is the radius of the Earth times radius of the Earth plus delta y. So those are going to cancel out. And some of this is going to start looking familiar. The change in gravitational potential energy, I'm going to have universal constant of gravitation, mass of the Earth. I'm going to pull out radius of the Earth squared, and I'm going to have delta y from in the numerator. And then since I pulled out the radius of the Earth squared, what I have left in the denominator is a 1, and then a delta y over the radius of the Earth. So this combination, oh, and I got rid of my m, sorry. This combination, universal constant of gravitation, mass of the Earth over the radius of the Earth squared, that is little g, acceleration due to gravity near the surface of the Earth. So change in gravitational potential energy is going to be m g delta y, and then this bit that's left over, 1 over the quantity 1 plus delta y over the radius of the Earth. Alright, now to make sense of this, I'm going to use the binomial expansion. This is in the appendix of your book, and you've probably seen it before. A plus b to the quantity n is a to the n plus n, a to the n minus 1 times b plus n times n minus 1 over 2, a to the n minus 2 b squared plus n minus 1, n minus 2 over 6, or 3 factorial, a to the n minus 3 b cubed plus dot dot dot. More terms, if needed. Now this quantity, 1 over 1 plus delta y over the radius of the Earth, matches our binomial expansion if a equals 1, n equals minus 1, and I'm going to let b equal x, which in our case is change in height in units of the Earth's radius. So our expression 1 over 1 plus x is approximately equal to 1 minus x plus x squared minus x cubed plus da da da. And you can sort of guess which way it's going. The next term is going to be x to the 4th. Now, if I want to say that the change in gravitational potential energy is just mg change in height, that means I'm keeping only this first term in the expansion, and that's going to be true if delta y over the radius of the Earth is very, very small. Okay, so radius of the Earth, 6,000 kilometers, delta y is a meter, then delta y over the radius of the Earth is very, very small. As delta y gets larger, then more and more of these terms could in principle become important. And if delta y is going to be certainly comparable to the size of the Earth, you wouldn't want to use this binomial expansion in any event. You would want to go back and just use our general expression. Okay? And that sort of sets the context. If you're talking about changes in height that are scales of meters, tens of meters, then you're completely fine truncating this binomial expansion. It's just the leading order term of 1. If you're talking about larger distances, and especially distances that are comparable to the size of the Earth, then these other terms, x squared, x cubed, are going to play a role. You can't neglect them, and so you shouldn't use this expression, which is a convenient expression near the surface of the Earth. You should go back and do the thing that is correct and has no approximations whatsoever.